strategies. So we'll today continuing the enzymes portion, catalytic strategies. Enzymes commonly employ one or more strategies to catalyze specific reaction. Okay. Among the best categorized mechanisms are general acid-base catalysis, metal ion catalysis, and covalent catalysis. So, three types of catalysis we are seeing: general acid-base catalysis, metal ion catalysis, and covalent catalysis. A combination of several catalytic strategies is usually employed by the enzyme. So we are seeing combination of these strategies. Good example of the use of both covalent catalysis and general acid-base catalysis occurs in chymotrypsin. So what happens in covalent catalysis? Covalent catalysis, the process of covalent catalysis involves the formation of reversible covalent bond between the enzyme and substrate. Although the covalent interaction are temporary, the substrate is bound to the enzyme during the course of catalysis. After the completion of the reaction, the enzyme returns to its original unmodified state. The proteolytic enzyme chymotrypsin provides an excellent example of this mechanism. Enzymes performing covalent catalysis near nucleophilic or electrophilic center. Nucleophilic center includes amines, carboxyl, hydroxyl, imidazole, and thio groups. These groups perform covalent nucleophilic catalysis and readily attack electrophilic centers of substrate, forming covalent intermediates. Typical electrophilic centers in substrate include phosphoryl groups, acyl groups, glycosyl groups. Covalent electrophilic catalysis is also observed but usually involves coenzyme abducts that generate electrophilic centers. Okay. Number 2, acid-base catalysis. Acid-base catalysis involves proton transfer. There are two kinds of acid-base catalysis: specific and general acid-base catalysis. In specific, hydronium ion and hydroxide ion act directly as the acid and base groups. In general acid-base catalysis, donors and acceptors of protons are other than hydronium and hydroxide ions. In such cases, the ionizable functional groups of amino acyl side chain and of cofactors, if present, contribute to catalysis by acting as acids or bases. Functional groups such as imidazole, hydroxyl, carboxyl, sulfhydride, amino and phenolic groups of amino acid act as acids or bases. As far as enzyme catalyzed reactions are concerned, only general acid-base catalysis can occur. A common example of general acid-base catalysis occurs in the hydrolysis of peptide glycan catalyzed by lysozyme. Specific acid-base catalysis is determined only by pH, and the buffer concentration has no effect. The general acid-base catalysis, however, the buffer may donate or accept a proton in the transition state and thus affect the rate. Next is metal ion catalysis, also called Lewis acid base. Many enzymes require metal ions for catalytic activity. These enzymes can be metalloenzymes. Enzyme binds to the metal ions very tightly or require the metal ions to maintain its stable native state, or metal activated binds to metal weakly. Metal ions can function catalytically in several ways. One role of metals in metal activated enzyme and metalloenzymes is to act as electrophilic catalysts, stabilizing the increased electron density or negative charge on a reaction intermediate that can develop during the reactions. Another potential function of metal ions is to provide a powerful nucleophile at a neutral pH. Enzyme activity: amount of enzymes that can be expressed as molar amounts or measured in terms of activity. Enzymes are usually present in a very small quantities, so a convenient method of enzyme quantification is a measurement of catalytic activity. Convenient method of enzyme quantification is the measurement of catalytic activity. Activity is then related to concentration. When enzymes are quantified related to their activity rather than their direct measurement of concentration, the unit used to report enzyme levels are activity units. There are two standard units to express the enzyme activity. Number one, enzyme unit U. The amount of enzyme causing transformation of 1 micromole of substrate per minute at 25 degrees Celsius under optimal conditions of measurement. One enzyme unit is equal to 1 micromole per minute. Number 2, Katal, K-A-T. The Katal is the accepted SI unit of enzyme activity. 1 Katal is the amount of enzyme that catalyzes the transformation of 1 mole of substrate per second. 1 Katal is 1 mole per second. 1 U is equal to 16.67 nanokatal. Difference in size. Oh my god. Next portion is the enzyme kinetics. The study of rate of enzyme catalyzed reaction and affinity of enzymes for substrate and inhibition is called enzyme kinetics. The general principle of chemical reactions apply to enzyme catalyzed reactions as well. In a chemical reaction of the form A plus B forms P, where A, B are reactants and P is the product, the rate of reaction can be expressed in terms of either rate of disappearance of one of the reactants or the rate of appearance of the product. The rate of disappearance of A is minus delta A upon delta T, whereas the del symbol symbolizes changes. Delta A is the concentration of parenthesis A is concentration of A in mole per liter and T is time. Likewise, the rate of disappearance of P is minus del B upon del T. The rate of appearance of P is del P upon del T. The rate of reaction can be expressed in the terms of these changes because the rate of appearance of the product and the rate of disappearance of the reactant are related by the stoichiometric equation for the reaction. The rate is this: minus del A upon del T is equal to minus del B upon del T is equal to minus del P upon del T. The negative sign for the change in the concentration of A and B indicates that A and B are being used up in the reaction while P is being produced. It has been established that the rate of reaction at any given time is proportional to the product of the concentration of each reactant raised to the power of a number of molecules that the reactant taking place. Small a, capital A plus small b, capital B forms a product. The rate is directly proportional to A from here raised to power A from here. times B from here raised to power B from here. So to take away this proportionality sign, we put a constant k here. So now the equation is R rate is equal to k times A raised to power A, B raised to power B, where k is the proportionality constant called the rate of constant. The exponents A and B must be determined experimentally. The law of mass action led to the concept of the order of reaction. The overall order of reaction is the sum of all exponents. The first order reaction is one which proceeds at the rate of proportional to the concentration of one reactant. Thus, for the first order reaction A to B taking place at the constant temperature and the pressure of a dilute solution, rate is equal to K A raised to power 1. The second order constant reaction is which proceeds at the rate proportional to the concentration of two reactants or the second power of a single reactant. Thus, the second order reaction of A plus B takes to B taking place at a constant temperature and pressure in the dilute solution, rate is equal to K A1 B1. The reaction is said to be first order with respect to A, first order with respect to B, and second order overall. Many common reactions are first or second order. It should be noted that the zero order reaction is also possible. This is one whose rate is independent of the concentration of any of the reactants. So for the zero order reaction A to B given by the equation, rate is K A raised to power 0 is equal to K. Kinetics of enzyme catalyzed reaction. When the rate, also known as velocity, of the enzyme catalyzed reaction is measured at varying substrate concentration, the rate depends on the substrate concentration. At a relatively low concentration of substrate, initial velocity V0 increases almost linearly with the increase of the substrate concentration S. The reaction reaches the maximum velocity Vmax with an increase of the substrate concentration, and it doesn't increase any further by increasing the concentration of the substrate. At high substrate concentration, V0 becomes virtually independent of the substrate concentration and approaches a maximum limit. The value of V0 at this limit is written as Vmax. This is saturation effect. Since a low concentration of the substrate, at low concentration, velocity is proportional to the substrate concentration, the enzyme catalyzed reaction is a first order reaction. At high concentration of the substrate, velocity becomes virtually independent of substrate concentration. Since the rate is no longer dependent on at the high substrate concentration, the enzyme catalyzed reaction obeys zero order kinetics. The plot based on reaction velocity versus substrate concentration shows the substrate saturation curve. So this is our Vmax. Why is my pen working like this? Oh my god. So what it is saying is this portion is V0, okay, all the velocity showing here, and this is the substrate portion. So V is linearly progressing and increasing with as substrate is added, concentration of substrate is increased, but after a certain period of time, okay, linearly increased in the first order reaction. Okay, But if it was zero order reaction, how max amount of how much substrate you add, concentration of substrate is increased, there is no change in the V value. So we say that we have reached a saturation effect, and here V naught is equal to V max. Okay, so let us see substrate. We have enzymes. Okay, we have little bit of substrate but more enzymes. After a period of time, we have enough substrate and we have enough enzymes for it. Two are still empty, but after a certain period of time, when there is so much substrate that there is not enough enzyme to cover for them, there is no change in the rate of reaction because the substrate is too much. At any point in an enzyme catalyzed reaction, the enzyme exists in two forms. The first E and the enzyme substrate complex ES. At low substrate concentration, most of the enzyme is in free form. The maximum velocity Vmax is observed when virtually all the enzymes is present as the ES complex. Under these conditions, the enzyme is saturated and its substrate with its substrate. So the further increase in the substrate concentration have no effect on the reaction velocity. This condition exists when the substrate concentration is sufficiently high with essentially all the free enzyme has been converted to the ES form. After the ES complex breaks down to yield the product, the enzyme is free to catalyze the reaction for another molecule of the substrate. Leonor Michaelis and Mold L. Minton proposed a general theory of enzyme action in 1913 after investigating the kinetics of the enzymatic reaction in which the enzyme invertase hydrolyzes sucrose, a disaccharide, into a monosaccharide, glucose and fructose. Michaelis and Minton proposed the following scheme of the single substrate enzyme catalyzed reaction where there is just one substrate binding site per enzyme, E plus S. Okay, so we see forward reaction has the constant K1. We are forming ES intermediate. Okay, so another forward reaction is going to take place where K2 is the constant and enzyme will take its own shape and the product will be formed. So it is a reversible reaction, so there is also K2, K minus 2. We have K1, so we have K minus 1 reversibles. Okay, if the product concentration is negligible, the formation of the ES from the product can be ignored. If the product concentration is negligible, the formation of ES from the product can be ignored. So here in this one, the this is not reversible. It is irreversible, so there is no K minus 2, right? In this reaction, K1 is the rate of constant for the formation of ES complex, Michaelis complex for the enzyme E and substrate S. K minus 1 is the rate of constant for the reverse reaction, dissociation of ES complex for free enzyme and substrate. K2 is the rate constant for the conversion of ES complex to product P and the subsequent release of product from the enzyme. They postulated that the enzyme first combines reversibly with its substrate to form ES. They say this is a reversible reaction. In relatively fast reversible step, the ES complex then breaks down to a slower second step. This is fast, but this is slow to yield free energy and the reaction product, free enzyme. When the substrate concentration becomes high enough to entirely convert the enzyme to ES form, the second step of the reaction becomes rate limiting. Because this is slow, so this will become rate limiting. And the overall reaction rate becomes insensitive to further increase in substrate concentration. Here, it has been assumed that the second reaction is irreversible. They are assuming that it is irreversible, that is, no product is converted back to substrate. The interpretation of the Michaelis-Menten model were redefined by Briggs and Haldane, by considering the steady state assumption. According to this, ES remains approximately constant over time. That is, the rate of formation of enzyme substrate complex equals to the rate of its breakdown. So when the enzyme and the substrate are first mixed after a very brief initial period, ES reaches a steady state level, that is dES upon dt is equal to 0. This change is 0. To derive an expression that relates the reaction velocity of catalysis to the concentration of the substrate and enzyme, the reaction velocity can be expressed as the product of the concentration of ES complex and K2. So V naught is equal to K2 concentration of ES from the law of mass action. Okay. The maximum reaction velocity Vmax is attained when the catalytic sites on the enzyme are saturated with substrate. At Vmax, ES is equal to concentration of ES is equal to concentration of enzyme total. Okay, so V naught is equal to Ks, concentration of ES is, so V naught is equal to Vmax is equal to K2 concentration of total enzyme concentration. The rate of formation and breakdown of ES are given by, so rate of formation of ES is this, rate of breakdown of ES is, we are taking both of them here and here. Okay, so we are taking both of them, minus 1 K minus 1 ES and K2 ES. Okay, the steady state assumption can be used to simplify matters. In a steady state, the concentration of ES remains. The steady state assumption can be used to simplify matters. In a steady state, and concentration of ES remains the same. The steady state is reached when the rates of formation and breakdown of the ES complex is equal. Okay, so we say K1 ES, the breakdown is equal to this, the rate of breakdown of ES. Okay, by rearranging this equation we obtained, we're just dividing them now. Okay, we obtain the Km, Michaelis constant. In the enzyme catalyzed reaction, the total enzyme concentration ET is equal to the uncombined enzyme plus the concentration of ES complex. ET is equal to enzyme plus ES complex. E is equal to ET minus ES. Okay, nice, understandable. Km, what we found from here, Km is equal to ES, concentration of E, concentration of S upon concentration of ES is equal to, we are substituting this E with this, so we got this and multiplied by S upon this. Okay, now Km, now we will multiply this with this and this, so we are getting this equation, right? So yes. So now we are taking it apart. So this minus this is what we are getting, and we'll reduce them, okay, eliminate them. So we are left with substrate here, okay. So Km is equal to V max substrate upon K2 Es minus substrate. How are we getting this? We know V max is equal to K2 times the concentration of total enzyme. Okay, so now Km is equal to V max. Now this, because this is equal to V naught. V max in times concentration of substrate upon V naught minus S. So what do we know now? V naught, we are taking this from here to here. How would we do that? We will do something like V max substrate V naught minus substrate. We will multiply, divide it here. V max substrate minus substrate V naught on V naught. I think so. I don't know if I'm doing something wrong, or we are doing something different here. Let me just think about it. Okay, I understood what they're doing here. They're not doing this. They're just simply taking Km is equal to V max substrate minus S, and there is one thing dividing here, V naught. So we are taking this substrate, and we are coming here is equal to V max substrate upon V naught. So V naught will come here. V naught is equal to V max substrate Km plus substrate. Easy peasy lemon squeezy. So after the whole thing, we are getting this as our end result. So this expression, the Michaelis-Menten equation, is the basic equation of enzyme kinetics. This equation says that the initial reaction velocity of the enzyme catalyzed reaction V naught is determined by two constants, Km, Michaelis constant, and V max, the initial concentration of the initial concentration of the substrate. Okay, we are thinking about three things here. To find out the initial velocity, we need to know V max, 1, the substrate concentration, 2, and the Km, Michaelis constant, 3. The following assumptions are made in driving Michaelis-Menten reaction. Number 1, the concentration of substrate is much greater than the concentration of enzyme. Understood. Number 2, the rate of formation of ES is equal to the rate of breakdown of ES. Understood. Number 3, very little accumulation of P, so that the formation of the enzyme substrate complex from E plus P is negligible, ignored, or any back reaction by which EP might form ES. The Michaelis-Menten reaction is therefore consistent, and the observed dependence of V naught on substrate concentration. According to this equation, the reaction velocity versus the substrate concentration shows that a rectangular hyperbola. All enzymes that exhibit a hyperbolic dependence of V naught on substrate concentration are said to follow Michaelis-Menten kinetics. So there is this graph. We have substrate concentration here, V naught here. We found a V max. The substrate is going like this. half of Vmax is here. So wherever it connects the curve and gives us the concentration here, and that is considered to be Km. The substrate concentration when the rate of reaction is half its maximum value, it is Km. Okay. When substrate is very substrate concentration is very smaller than Km value, then V naught is directly proportional to S. Substrate concentration is very smaller than the Km value, right? So we are seeing this portion. So we say V naught is directly proportional to concentration of substrate. At low S, the S term is in the denominator becomes insignificant and simplifies to V is equal to V max S upon Km, and V naught exhibits a linear dependence on S. When S is way greater than Km, S is like here, okay, then V naught reaches the V max. Okay, we can see it through graph and we can see through the Michaelis-Menten equation, it is equal. Okay, so when S is equal to Km, then V naught is equal to V max by 2. That is the statement of finding out the Km. This gives the practical definition of Km. The substrate concentration at which the reaction velocity is half maximal. Therefore, if an enzyme has a small value of Km, it achieves maximal catalytic efficiency at low substrate concentration. Another interpretation of Km relies on the assumption that the original Michaelis-Menten scheme of the reaction E plus S, K1, ES, K2, E plus P, ES, K minus 1, E plus S. Km is equal to K minus 1 plus K2 upon K1. K minus 1 plus K2, the dissociation of ES upon K1, the formation of ES. If K2 is much smaller than K1, K minus 1, the Michaelis constant can be expressed as K minus 1 upon K1 is equal to Ks. Km is equal to the dissociation constant Ks of the ES complex. Since Ks is the dissociation constant of the complex, as Ks decreases, the enzyme affinity of the substrate increases. Lower value of Km describes the greater affinity of the enzyme for the substrate. Km is therefore also a measure of the affinity of the enzyme of its substrate. If K minus 1 is much greater than K2, Km is expressed as mole of substrate per liter. Km is unique for each enzyme substrate pair. Different enzymes that act on the same substrate have different Km values. For most enzymes, Km lies between 10 raised to power minus 1 and 10 raised to power minus 7 m. The Km value for an N also depends on the environmental condition of such as pH, temperature, and ionic strength. Catalytic constant.